Good morning everyone, my name is Andrea Stertin, and in this presentation I will discuss the main 3D acquisition techniques applied to cultural heritage, as well as the theme of our heritage modeling approach. So why use 3D in cultural heritage? First of all, for documentation. Three-dimensional models allow high-detail recording of objects, architecture, and sites, integrating metric, visual, and contextual information. Secondly, 3D supports analysis. It can be used for scientific research, conservation planning, and heritage enhancement. Another fundamental aspect is digital preservation. The 3D model becomes a form of digital memory, particularly useful for counteracting the effects of decay, natural disaster, or conflicts. Finally, 3D is a very powerful communication tool. It makes heritage more accessible to expert institutions, students, and the general public. In general, we can distinguish three main approaches to 3D modeling or reconstruction of cultural heritage: source-based modeling, reality-based modeling, and an hybrid approach. In source-based modeling, modeling is carried out starting from historical and documentary sources, drawings, historical photograph, maps, description, and historical or incomplete surveys. This approach is useful, for example, for reconstructing buildings that no longer exist, earlier historical phases, or lost configurations. The reliability level of the model created depends heavily on the quality, quantity, and the consistency of the available sources. For this reason, it is important to clearly distinguish what is documented from what is interpreted. In any case, since the result is not based on direct surveys, it cannot achieve extremely high accuracy. The reality-based approach is instead based on reconstruction from survey data, acquired directly from the object or site. This includes techniques such as laser scanning, photogrammetry, and topographic surveying. In this case, the result generally consists of a point cloud or a textured mesh. Its main strength is that the model maintains a direct relationship with the real geometry of the documented heritage asset. An hybrid modeling combines the potential of the approach just described, supporting the creation of an accurate model with associated informations. Reality-based data provide the geometric and metric basis, while historical and documentary sources make it possible to integrate and enrich the model with different kinds of informational content. In particular, this is the case of the heritage BIM models, where BIM stands for Building Information Modeling. The 3D model should therefore not be considered merely as a geometric form. It can become an information container. Identifiers, metadata, classification, and relationship with digital catalogs or information system. This step is fundamental in moving from a simple 3D model to a model that is truly useful for the knowledge, management, and enhancement of heritage. Let's now focus on reality-based modeling. A first key point is that surveying is never neutral. Every acquisition campaign is a methodological construction. Every choice, whether implicit or explicit, determines the type of knowledge that the final model will be able to support. For this reason, surveying is not an uncritical collection of data, but a form of oriented interpretation. It's important to define, from the outset of the objective, the required levels of detail and accuracy, and the future use of the model and of the knowledge base created during the process. There is therefore no rigid workflow that is valid for every case. In general, we can identify several phases: defining objective, assigning operational conditions, selecting techniques and instruments, and organizing the team and activities. The main acquisition techniques for three-dimensional reconstruction can be grouped in three complementary families: range-based, image-based, and topographic techniques. In practice, these techniques are often integrated. Range-based method can provide dense and highly accurate point-based geometry. Image-based methods are used for collect geometrical data with high chromatic detail, while topographic techniques are particularly suitable for acquiring highly accurate point information for metric control and georeferencing purposes. Let's begin with the range-based methods. These techniques rely on active sensor, which emits their own signal and use it to estimate the distance between the sensor and the target. They are particularly suitable when accurate and reliable geometric documentation is required. The main result is usually a point cloud, that is a very dense set of point elements with three-dimensional coordinates. Range-based systems can differ according to their measurement principle, such as time of flight, phase shift, and triangulation. Its principle involves a different balance between range, speed, and accuracy. Time of flight derives the coordinates of point in the scene by calculating the distance from the sensor based on the measurement time it takes for a laser pulse to reach the surface and return to the sensor. It's suitable for long-range survey, especially in outdoor or architectural contexts. Phase shift, instead, is based on measuring the phase difference of a modulated laser signal. Due to its accuracy, precision, and measurement speed, it's often used in indoor architectural or medium-range environments. Triangulation methods project laser or structured light onto the surface and calculate 3D position from the geometry between emitter, sensor, and targets. They provide high accuracy at short range, making them suitable for close-range digitization. In addition to the measurement principle, we can distinguish several instrumental configurations. Tripod-based systems are a fixed station laser scanners used for accurate survey of built environments. Mobile systems are mounted on moving platforms such as vehicles, both terrestrial and aerial, robots, or backpack systems, and they allow rapid and continuous mapping of large environments. Handheld systems are more flexible and suitable for close-range surveys, small objects, and complex details. The typical workflow of range-based methods starts from scan acquisition. In the slide, we can see an example of terrestrial laser scanning acquisition mounted on a tripod. Each scan acquires the surface of the heritage asset visible from the position of the instrument. Several scans are therefore carried out from a strategic position in order to acquire multiple portions of the asset surface. To obtain a complete model, these scans must be aligned through the registration phase. The next step is filtering to remove noise, erroneous points, or unnecessary elements. Once these phases are completed, scan unification is often carried out, with the aim of obtaining an unified point cloud with controlled density and reduced file size. Optionally, a mesh model can be generated, and if color information are available, it can eventually be textured. Range-based methods have several strengths. They offer high accuracy, rapid and dense acquisition, and in geometry reconstruction, they don't depend on ambient light conditions. However, they have also some limitations. Instruments costs can be very high. Some surfaces are problematic, for example, reflective, transparent, or very dark surfaces, and color information is often less rich than the one produced by image-based methods. Let's now move on to image-based methods with particular attention to photogrammetry. Unlike range-based systems, these use passive sensors, such as photographic cameras, which do not emit their own signal, but records the light reflected by the surfaces. The 3D model is reconstructed from multiple images of the same subject, acquired from different viewpoints with good overlap and distributed coherently around the object. In the case of architectural or archaeological site, it's normally the camera that moves around the subject. For a small object, instead, as in the example shown in the slide, the opposite can happen. The camera remains fixed and the object is rotated on a turntable. The first computational step is structure from motion. The software identifies corresponding points visible in multiple images, estimating the position and orientation of the cameras, and generating an initial sparse three-dimensional structure made up of so-called tie points. The next step is multi-view stereo, which uses the already oriented cameras to estimate for each image a depth map, a map in which each pixel is associated with a distance from the camera. The slide shows an example of a depth map. By interpreting the depth map generated from multiple overlapping images, the software produces a denser reconstruction, capable of describing the surface of the object or site with greater continuity. After looking at the basic principles, we can translate them into the operational workflow of photogrammetry. The first step is camera alignment, based on structure from motion. This step is fundamental because it defines the geometric consistency of which all the subsequent processing is based. Starting from the aligned cameras, the process continues with dense data generation through multi-view stereo. The software calculates depth map and from these can generate a dense point cloud, often also associated with color information. In some application contexts, the dense cloud can already represent a useful final result. The workflow can then continue with the generation of a continuous surface, known as a triangulated mesh. Depending on the software and the chosen processing path, the mesh can be built either from the depth maps or from the dense point cloud. Once the model has been generated, the already-oriented photograph can be projected onto it to obtain an applied texture. Compared with the point cloud alone, the textured mesh offers a more continuous and visually readable representation of the object. This result is particularly useful for communication enhancement, the reading of surface detail, and some forms of qualitative analysis. The great advantage of image-based methods is the richness of visual and color information. Moreover, photogrammetry is flexible. It can be used on small object, architecture, landscape, or archaeological sites, and it often requires less expensive equipment than range-based methods. On the other hand, it depends heavily on image quality, image distribution, and lighting condition. Surfaces that are reflective, transparent, or lack of texture can also be problematic. Furthermore, to obtain a metrically reliable model, it's often necessary to integrate external scale or coordinate references. Let's now move on to topographic techniques, which play a leading role in a three-dimensional reconstruction process. Topographic techniques generally do not produce dense or visually rich data, but they are essential for ensuring metric control, scale, and spatial reference for 3D models. GNSS, which stands for Global Navigation Satellite System, includes satellite systems such as GPS, Galileo, GLONASS, and Beidou. Through signals received from multiple satellites, it makes it possible to determine the position of points on Earth's surface within a geographic coordinate system. The total station, instead, is a terrestrial surveying instrument that measures angles and distance to a specific point, often materialized with prism or targets. These measurements are used to obtain very precise three-dimensional coordinates useful for metric control and building a local reference network. The integration of GNSS and total station therefore make it possible to connect point clouds and mesh derived from range-based or image-based techniques to a global geographic reference, while at the same time maintaining high precision local metric control. The limitation is that, taken individually, these are sparse measurements. They do not describe the entire surface as a point cloud or a mesh does. For this reason, they are often support techniques, but a session support, especially for projects that require accuracy, comparison over time, or integration into geographic information systems. In recent years, techniques based on artificial intelligence have also been emerging. However, it's important to clarify that AI cannot replace traditional acquisition techniques or source-based modeling. Rather, it extends some of their capabilities. It can help with reconstruction from incomplete data, advanced visualization, automatic or semi-automatic interpretation, and the processing of a large amount of data. Some examples of AI techniques adopted in recent years in the field of cultural heritage are neural radiance fields, the so-called NERF, generative AI for 3D content from text or from a single image, monocular depth estimation, and semantic segmentation. At present, these techniques appear very promising, but they still present several critical issues. The strengths of AI include the ability to manage incomplete dataset, automate repetitive operations, improve visual realism, and analyze large amount of data. However, the limitations are significant. Metric reliability is often reduced or absent. They may produce implicit representation, such as NERF, rather than 3D true models. They are based on black box models in which the user has limited control over the process, and they depend on training data with possible biases. For this reason, AI should be seen as a complementary tool, not as a shortcut that removes the need for method control and documentation. We now come to the concept of aware heritage modeling. The digitization process does not end with the generation of 3D model. After acquisition and processing, it's necessary to manage, organize, and document the data produced. This means choosing suitable and interoperable formats, associating accurate metadata, and also documenting paradata. Formats are important because they determine whether a model can be reused in different software or contexts. Metadata describe the data, who produced them, when, with which technique, at which resolution, and which reference system. Paradata instead describe the process, why certain choices were made, which interpretations were applied, and what limitation the model present. Without this information, even a very accurate model risks losing value over time. This topic is linked to FAIR principles: findable, accessible, interoperable, and reusable. Data must be easy to find, clearly accessible, usable in different systems, and reusable in very contexts. In cultural heritage, this is particularly important because digital data do not serve only the immediate project, but can become a resource for future research, conservation, education, and enhancement. The central point, therefore, is not to choose the best technique in absolute terms. Every method has advantages, limitations, and fields of application. The real objective is to build a knowledge base grounded in a conscious process, understanding the limits of the instrument, documenting choices, and producing reliable and reusable models. In this sense, the goal is not the 3D model itself, but the construction of solid and lasting knowledge about cultural heritage assets. And that's all. Thank you for your attention. Enjoy our heritage modeling, everyone.